Hello all, welcome to the video lecture series for the subject operating system. Now I am going to explain you all about the second most effective algorithm in CPU scheduling, that is shortest job first. Now in this shortest job first, we are separating that into two different processes. One is non-primitive, another one is primitive. So let me tell you what is non-primitive in detail. Every process, right, will take full CPU time. Say for example, if a process arrived at a time and its burst time is maximum than the previous one and the next one, so it once it is getting into the CPU, unless it complete the task, it will never leave the CPU in between. That's a point. So this is we can say it as non-primitive process, right? So this shortest job first will have two different aspects. One is non-primitive, another one is primitive. Let's get into the topic with non-primitive. So for example, here the shortest job first algorithm have some four process, P1, P2, P3 and P4, and the burst time has been given here. Now this is example number one. After I explain this example number 2 with arrival time, that's a difficult one, you can do this as a activity, right? Let me get into the process directly. Now here you can see that the second example I have taken process ID, arrival time and burst time for 5 process, and the arrival time for 1, 2, 3, 4 and 5 has been respectively given here. This is the burst time, right? Now what is this shortest job first? Among whoever is arrived first and whoever is arrived at the similar time, that doesn't matter. Only the burst time has to be calculated, and also at the same time we need to check the arrival time. Say for example, among these 5 process 1 burst time is very low and it arrived time is 3. So the next process is P2 and it's arrived at 1. Before this P1 it is arrived and its burst time is bigger than this process 1. And you can check the next one, process 4, its arrived time is 0 and its burst time is bigger than P1 and P2. That means whoever comes first will be given the chance. At the same time, it will look for the burst time as well. That's a point. So we need to look for both arrival time and also the burst time. If you are drawing a chart based on the burst time and you will be taking P1 because its burst time is very low comparing to all the process. If you take this and allocate a CPU, that means it is wrong. Why? Because comparing to P1, it is coming at the time of 3, and P2 before P1 it is arrived. Before P2, P4 is arrived. Even though it is burst time is higher, but it is arrived. So it will take the process and it will run, right? So we are going to check how does this process works for non-primitive first. Okay, non-primitive in the sense a process will take. So whatever I said, you just take these values and apply for primitive or non-primitive. One by one, I am going to explain you. So let's take who comes first here, P4. Okay, so P4 is getting inside, so you can check the Gantt chart, right? It is a non-primitive in the sense once the process task, full time of the CPU will be taken to complete this task. It is not leaving the CPU unless it completes its job. Now say for example, who arrived first here? P4, because the arrival time is 0. So the Gantt chart has been drawn based on that. Now P4 is arrived, and what is the burst time for P4? Here it is. P4 arrived, burst time is 6. So I told you in non-primitive, once it is getting a CPU, it will not leave the CPU unless it completes its job. So the burst time is 6. So P4 will run from 0 to 6. So P4 is over. Who comes next? P2. Because its arrival time is 1. So even though it is arrived at 1, it has to wait this P2 has to wait for P4 to complete because it's a non-primitive process, non-primitive scheduling. So P1 arrives and it is taking this particular CPU. What is the burst time for this P1? Here it is. Yeah, now you can check it. Now by this time, that is, I forgot to say this, by this time 0 to 6, you can check that all the process has been arrived. P1 arrives at 3, P2 arrives at 1, P3 arrives at 4, and P5 arrives at 2. Within this timeline, after this P4 completes this task, and it is checking that all the process has been arrived before the timer called 6. That's a point. Now you don't want to check any of this because all the process has been arrived before this P4 has completed its task. Now at what time the P4 has been completed? It starts at 0, ends at 6. You can check that. Now you can check that all the process arrived before 6. You can check it. So by the time this P4 completes its task, all the process has been arrived. That means we need to check only the burst time after this P4 has been completed its task. Now who comes which particular shortest job first, right? Which burst time is very less will be considered treated first. So P4 is already over, no problem. Who comes next? Absolutely P1. Why? Because it has the least best, that is burst time. So you can check it. P1 is taking the CPU and it starts at 6. Burst time is 1. So 6 plus 1, 7. So what is the next burst time is very low here. So this is also here. So 4, 2 and 3. Who is shortest job here? 2. So 2 is getting inside. It starts at 7 and 7 plus 2, 9. So P3 is also over. And again now P5 is coming. Why? Because 4 and 3. Which one is shortest job? This one. That is P5. So P5 is coming inside. 9 plus 3. 9 plus 3. 3 is the burst time to complete this P5. So 9 plus 3, 12. So P5 is also over. Now finally who comes here? P2. P2 comes here and its burst time is 4. It takes the full CPU finally. So 12 plus 4 burst time. The P2 has been complete the task. Right? Now this is how the process has been done. See here the only checkpoint you can see here it is. Who comes first will be treated first because this is a non-primitive process. Along with the same time, if P4 by the time it completes the task, it is checking all the arrival time. If it is checking all the arrival time, by the time P4 completes, everybody arrived. All the process arrived. So now it will check only the burst time. That's a point, right? This is in non-primitive. Right? So now you can calculate here. The calculation has been given. Waiting time has to be calculated here. You can calculate turnaround time based on the formula, right? And you can check it the waiting time here. Now waiting time is equal to start time minus arrival time. What is the start time for P4? You can check it over here. So here, what is the start time for P4? 0. What is the arrival time for P4? Here also you can check 0. So 0 minus 0. The answer is 0. So it is calculatively, numerically proven that P4 is not waiting for anybody. You can check it. See here, P4 arrives 0 and it starts. It is here it is. So P4 is not waiting for anybody. It starts exactly. This is the numerical method of proving that no process is waiting. Sorry, how many process is waiting, how many minutes or seconds based on the CPU structure. So P1 comes at 6. Start time for P1 is 6. You can check the Gantt chart and its arrival time is 3. So it is waiting for 3 seconds or minutes. P3 comes at start time is 7 and its arrival time is 4. So P3 is waiting for 3 seconds. P5 comes at 9 and its start time is 9 and its arrival time is 2. So the total waiting time is 7. P2 starts at 12 and its arrival time is 3. So P2 is waiting for 9 seconds. So let's see. I am going to take this P2 because it is waiting for a longest period of time, right? So I am going to prove that how this formula works. Here P2 is starting time for this P2 for execution is 12 minus what is the arrival time for this P2? Arrival time here you can check it 1, right? Sorry, arrival time for this P2 here it is 1. So 12 minus 1. So it is waiting for almost, right, P2, right? It is waiting for 11 minutes. right? So this is how this process has been adopted over here. So we need to check each and every process one by one, and the values has to be calculated. Okay, so I'm just giving the overview of this. You can just check it. This is the second example I have taken with arrival time. You can solve this particular thing. It's a get question. So you can solve this example number 1, and you can do that because there is no arrival time here. So directly you need to check only the bus time. You can take this, draw a Gantt chart only based on the bus time. So waiting time for process 1, process 2, 3 and 4 is 0. By default it is 0. So this is the overview. We have drawn the Gantt chart and we have drawn this particular thing also. So here the process 12 minus 1. Why? Because P1 arrived at 1. It's a mistake. 11. So it is 11 divided by 5. So you can calculate the total average waiting time for each and every process divided by 5. Okay. So now again I am just getting into the primitive process. Now this is the end of this video. I will explain you about what is SJF, that is shortest job first, in primitive scheduling. I hope you understand the video. Thank you.